Now there will be the second presentation by Marc Stöttinger from Rhein-Main University of Applied Science, and title is Voronoi-based multidimensional parameter optimization for fault injection attacks.
Thank you for the kind introduction. The talk I'm going to give here is majorly the work of one PhD student of our university. And in this talk, we will show, let's say, a search strategy, which is semi-deterministic compared to previous work. Most of the work before, when they're tackling to identify parameters or multidimensional parameters for fault setups, using heuristic approaches. Here we present approach, which is, I say, semi-deterministic. We will know why when I present the scheme. But before I start with explaining the scheme, I will bring up a motivation, which is maybe not so much known to a lot of you, because actually the motivation comes from a law enforcement setup and such an application. And after that, I will describe the methodology we use, followed by some simulations we did, followed by some experiments to verify this, the proposed methodology. So, yeah, I said I will bring up a maybe interesting use case for, let's say, when you look from a forensic perspective, usually when there's a crime happened, you take forensic material, most likely physical, but nowadays more electronic devices get into court when it gets to gather evidence. And in this setting, when there is a permit to extract data from a judge in order to get some evidence in a court case, you need sometimes to get around security schemes on such device like a smartphone or like a encrypted USB stick. Some of the devices use software to do the security to protect the data. Some of them are more mature to say and use hardware, let's say, protection mechanisms. And for that, you need to go not on software exploits for sure, you need to go more likely on attacking the hardware, which is protecting the scheme. And therefore you can either go with invasive attacks for sure to tackle the or to circumvent this hardware security measures. You can go for semi-invasive attacks like laser fault injection attacks and non-invasive attacks, for instance, voltage glitching attacks. Yeah, but how to move on? Next slide. Okay, so when you talk about this different ways how to tackle the hardware security scheme, we can say, okay, when you go for non-invasive attacks, which is most likely the simplest one, because we have not so many parameters to fit, we change the environment in which the target processes. For semi-invasive attacks, we need to get a little bit more hands on the device. We need to most likely to open it, to thin the substrate. We have more parameters to consider. And in case the device has some countermeasures against fault detection or simple, let's say simple fault injection attacks, we need to fiddle more on the parameter sets to actually get our, to circumvent the hardware, which means the more professional device you have, the harder to actually get your parameter set. And you cannot just brute force all different parameter sets. For example, when you go for laser fault injection, you would have the position, for instance, the strength of laser beam, duration, for instance. So these are just 4 parameters, so to say. And this can increase if you take more parameters into consideration or you do a second order attack, for instance. And therefore, you cannot go through all the parameters because it takes too much. Now comes the interesting point when you talk about this law enforcement setting. Next slide, please. So when you look at fault injections from academia, you just want to show that this scheme is secure. You can it's secure, unsecure. You just need to find one fault, and then you show the the system is broken. However, in a evidence case, it's a little bit more tricky because you need to assure that you only extract the data you're allowed to extract and you're not altering the device, which means you cannot destroy the device or maybe induce some additional data into it. So you need to get on the spot more or less the data extracted, maybe to circumvent maybe an if else check, and do not change anything else in the device, which means it seems quite hard. And the way to achieve that is normally you have a training device which is similar. You train with this device, and then you transfer your parameter set to the actual evidence device and extract the data, hopefully. So it's something like a template setting, you know, for session analysis. So, but there's additional challenges. So when you get a device for analysis, you usually do not have data at hand. And when you look at professional devices, there's much more, let's say, countermeasures inside which you do not know how they're working. You do not get the information. So it's more like a black box. And on top, if you compare the training device to the evidence object, you do not know the condition in which the evidence object was run. So you do not know the state of the aging state of silicon maybe. So it could change also some parameters. And this actually drives us to the point that we need to find a method to get not only one parameter set that works on a training device. We would need actually a set of parameters that works on the training device, that it can be tested efficiently on the evidence object. Okay, and how to tackle this is basically what you're going to talk about now. To give a motivation, what you're doing, we actually came up with the idea, okay, looking to how you can partition a space. So actually we looked into Voronoi tessellation, and the idea is quite simple actually. So let's assume you have a space here and you have some sample points. You know, these sample points give you some kind of information. Now the question is where you take the next sampling point to get more information. I mean, ideally you would say you should maybe check between these points or these points, and there the Voronoi tessellation algorithm gives you a nice approach, because it builds you a cell-like structure by you taking the most adjacent points, for example these two, takes a distance, and in between this distance you make an orthogonal line, and this you make for all dimensions, and thereby you have tilts, you have a polytope structure, and now you can partition your overall map into polytopes and say, okay, the most likely outcome that I can get more information is on the line actually. So therefore it's like a partitioning algorithm. And this Voronoi tessellation does not only work like here in a two-dimensional space, it actually works in an n-dimensional space. And another advantage is in fault injection setup, some parameters are influencing each others. So when you change one parameter, you might affect the outcome of the other parameter as well, which means you need some kind of search strategy to handle with this. And with this approach of using Voronoi tessellation, you can search independently in the multidimensional space, because you do the partitioning between each dimension for an optimal, let's say, lookup space. And how to transfer this to fault injection, we'll give you an example. Instead of just say we have sample points, we label now sample points in sample points where we have a fault, and we have normal operation, like this blue one. So, and so in the beginning, we just put some test points, we test some parameter sets on B and on A, and the outcome is we get a fault or we do not get a fault. And when you now apply this Voronoi tessellation to it, we actually get polytopes, yeah. But the most interesting line of the polytopes is in between these two classes. So which means most likely looking into onto points which are on the line are more interesting, because these are the border area where the device works or does not work. Which means when we now make a new test point, for example here, and run the algorithm again, we get a new map. So we can, let's say, iteratively make our map more precise. And the nice thing is that you can actually do this not in a two-dimensional case like here, you can do it in an n-dimensional case. So how to transfer this to a fault injection setup. I will now motivate with a very simple setup with voltage glitching. So when you look at voltage glitching, you actually have not two operations for your fault injection setup. You have actually three classes you're interested in. You have one class where normal operation happens, so you inject the fault, nothing happens. Then you have the class you inject the fault, you get the brownout detection area, your device shut down. You do not want this case. You actually want to get into this interesting region where you inject a fault and the output is altered. So, which means you're very interested into getting into this area. You're interested in getting into this green area, but the borderline between blue and green and red and green are the things you want to identify, because they are most likely in between these two borderlines you have parameter switch works. And you can just try additional strategies on that, because when you try to set up polytopes between these two lines, you might get into with testing into this brownout detection area. So thereby you can also do a little trick by mapping the three classes into two classes in order to just detect only the upper boundary area. I will show it on the next slide. So when you say you want to build now, let's this Voronoi testination algorithm run and set up new points and do no mapping, you will end up with this. You will find some points which are in this area which you have normal operation, and some in the interesting area, and some in the area where you have with the device shut down. If you remap this, let's say, normal class area, or this interesting area normal class, you will end up that the borderline of interest will be actually at the exact borderline here between it works or it doesn't work. So, which means you have the parameter sets on the edge that it processes with an error, or it doesn't process. When you now map it to different, so that you say that the class of interesting region and doesn't work, you map together into one class, and compared to the class of it's working, you actually get the upper bound, which means you do not shut your device down so often, because you get the result back, it's working, or it's the injected error does not shut down the device, but change the output of result. The next thing I would like to discuss with you, because you from the beginning I said the most interesting point where to look up to get the next point into this map to actually probe is in between two tiles. Now the question is it really the best spot? Because actually when you're getting on the line, on the edge of two polytopes, it can be the exact barrier or not, because then you need to reiterate. Also, when you put 2 points on the same edge, you get no additional information. Therefore, if you add noise, you can actually increase a little bit your search strategy, because you set a point maybe in this area or in the other area, so you actually shrink or widen the other class. And therefore, therefore you get the speed up, because you do not need to reiterate so often. And in addition, you will see later on the simulation experiments, if you have multiple areas where a fault parameter set works, this can be then identified more easily. So do not run to the issue that you have only one parameter set which is similar to a local maximum. You can actually go to an absolute maximum for finding the parameter set. To show you how this works, we run a simulation where we said, okay, we define a parameter set A and B, and in the center of this set, we defined this area that the device is not working. Then we had a ring outside where the device in the simulation, where the fault was successful, but it was not shut down, and the outer part where it just had normal operation. So we want to find out, okay, can you really use this Voronoi mapping scheme to find any arbitrary form of parameter sets? And as you see here, we can really identify any different form of parameter sets. So one, we have no mapping, so we identify all three classes on one. But there you see the issue that the green dots, which show the region of interest, is very thin and might not be the complete solution space we can afford with a certain amount of testing points. When we add Gaussian noise, so when I said we do not get directly on the borderline of two polytopes, we actually get more interesting points we can observe on this fixed number of sampling points. And then comes the other point into place where we said, okay, if we map everything to failure, meaning we differentiate only between operation and not operation, we can reduce the amount of shutdowns dramatically to 2 only. So when you have the normal operation mode, we have 3, in this simulation, 3 test samples where the device shut down. And when we just map this to failure, we reduce it to 2. The other way around is we map everything to running with a failure. So we have more actually points where we shut down the device. So as you see, we can thereby find any arbitrary parameter form setting on 2-dimensional space. So next step, we want to see how it performs on a multidimensional space. So what we actually did, we set up a hypercubic space. I will show a plot only in 2D. So we said we have 2 parameters we're changing, and we observe only the 2 parameters, and the other 4 parameters are also changing, can also be changed. But you need to keep in mind that when you change when you increase the dimension of your parameter set, the success rate to be successful gets smaller because they depend on each other. So again, in the center, we put the area of failures where the device shuts down. Then again, a ring of success, and everything else outside we put as normal working mode. And if you see here in the left side, this is now a 2-dimensional slice cut of a 6-dimensional problem. We can still identify parameter sets for A and B independently of the 4 other parameters which are running with this algorithm. And now comes to place what I said with do not run into local maximums or minimums. In the next experiment, we actually defined 2 spaces. Let's say two spaces where failures should be, or where you could inject failures, or let's say parameters where you inject failures, and started by one side, and due to the noise you increased and the randomly selection point of using a different starting point, the algorithm actually can identify both of these parameter sets. Yeah. So, but it comes with a cost. For 2-dimension SSC, the algorithm is quite efficient on a success rate up to 100% quite easily after, let's say, a reasonable number of test points. Furthermore, you increase the dimension, the more test points you need for sure. Yeah. Please keep in mind when you have 2 parameters and 1,000 test points, we had about 1,000 edges to handle. With the same 1,000 test points, we go to 6-dimension, we have 100 million edges to test. 100 million. So it takes a long computational time. This is also a little bit kind of drawback because since this is a more deterministic approach, we need to actually go through it. The next step was we were thinking about, okay, can we also use it for spatial optimization? You use, for instance, for EM fault injection, where you want to find out which kind of region is of interest. And there we used this experiment from Reis Ali et al., where they identified useful positions for EM fault injection with a 5-dimensional model. We run the data through the algorithm, and actually the algorithm also identified the same spots. And there you can also see a drawback on this scheme, because you only identify the corner cases or the outliers. So, which means when you go only for 2 classes, which means fault is injected, fault is not injected, you have no clue about the inner part of this area. Yeah. So this approach using Voronoi only gives us the corner cases. Yeah. Okay. So after you run all the simulations, we thought, okay, let's run a real experiment. So we ran a voltage glitching experiment. We had a small LPC 2129, and just did a Kropa voltage glitching injection attack, but actually not only used 2 dimensions like voltage, fault voltage, and duration. We actually put also the IO voltage and core voltage. We also changed during operations to see if this has an effect. And sorry, the fault delay as well. So in the end, we can compare a 3-dimensional model, which is rather straightforward, or let's say known, to a 5-dimensional model to see if the other, let's say, effects, if the other voltages also have an effect on the parameter set. And if you can see here, in all 3 cases, the algorithm was able to identify some parameter sets based on the voltage, fault voltage and fault width, where the device actually, where a fault was injected and successfully injected. Interestingly, if you see here, even for the 5th-dimensional approach, where you have also changed the core voltage and the IO voltage, we actually got more points on different area perspective. No? So this brings me to almost to the end. To summarize, so in this paper, we present a normal semi-deterministic approach. Semi-deterministic because you still need this kind of randomness, this Gaussian noise and Gaussian tunneling noise, to ensure that you're not running into a local minimum or maximum. We have shown that with experience and simulation, it seems to work quite effectively. And we have no restrictions regarding the parameters. So we can search almost parallel, so to say, almost. And the nice thing is we can handle arbitrary forms and shapes. The drawbacks a little bit is, as said already before, you just have the borderlines. You just have, let's say, the outliers you can identify. For multiple regions, you need some random points to select. Yeah, that comes when you compare to previous work where genetic algorithms has been used. There the idea of mutation is more or less taken, that you need some kind of random points to take at the parameter set to ensure that you're not ending up in a local minimum maximum. And it takes quite a time of computation if you go to higher dimensions. So for future work, we would like to speed up. So thinking about strategies how to process this more efficiently in high dimensions. Also, when you think about the dependency between certain parameters, can we also count that we are even smarter to look into different dimensions or combine them? As I already said, we should still need some randomness. So the idea is to combine this region with genetic algorithms to have a more heuristic approach, or maybe some kind of federal learning approach. And when you, what we haven't done so far was using a 4AM positioning in an experiment, but there we see also efficient improvement in efficiency about the positioning time. So there should also be considered some, let's say, restriction selections on parameter sets to be more efficient or less time consuming. And this concludes my talk. Thank you.